Here's one of the most elegant and powerful results in linear algebra, the dimension formula. This formula reveals the relationship between the sizes of subspaces, their sum, and their intersection. Our goal in this video is to prove this formula. Okay, let's start. Before we start, remember, in this video, V is always a vector space over a field F, and its dimension is finite, and W, W1, W2, and so on are subspaces of V. Now, let's really start. First, Theorem 1 is a form of the basis extension principle. So, let G be a set of vectors v1, v2 up to vk, which is a basis of a subspace W. Then we can add some more vectors from v, vk plus 1, vk plus 2 up to vn, such that this combined set from v1 to vn is a basis of the entire space V. How do we know that? Let's quickly go through the proof. Let the set of vectors w1, w2 up to wn be a generator of V. So there are n vectors that spans the entire space V, and let B be the set of these vectors from v1 to vk that spans the subspace W. Then we apply the following algorithm. If the entire space V is spanned by B, then we are done. This means this B is a basis of V. Otherwise, go to the next step. So step 2, find a Wi from this set that does not belong to the subspace spanned by B, and update this set B by adding this Wi. And we go back to step 1. And step 1, we check if B spans the entire space V. If it does, then we are done. Otherwise, go to step 2, and we repeat this over and over again until eventually this holds. So at that point, B is a basis of the vector space V. Now, let's establish some crucial properties related to the dimension of V, which we denote by n. First, if you have a set of m vectors, so w1 up to wm, that are linearly independent, then n is greater than or equal to m. This means the dimension n is the maximum number of linearly independent vectors you can have in this space. The proof is quite simple. Since w1, w2 up to wm are linearly independent, they form a basis of some subspace W, let's say. And by the basis extension principle, we can add some more vectors to make a basis of V. And the dimension of V is n, and we added some vectors to these vectors, so m is less than or equal to n. And we are done. Next, if you have a set of m vectors that generates the entire space V, then n is less than or equal to m. That means the dimension n is the minimum number of vectors required to generate the entire space. Again, the proof is quite simple. Since the entire space V is generated by these m vectors, we can pick some of them to make a basis of V. But the number of picked vector is at most n, because the dimension is n. So n must be less than or equal to m. And we are done. Building on those theorems, we arrive at the powerful set of equivalences for a set of n vectors in the n-dimensional vector space. First, this set of n vectors is a linearly independent set of vectors. And second, this set generates the entire space V. And third, this set is a basis of V. So 1 implies 2, which implies 3, which implies 1. So they are equivalent to each other. Let's walk through the proof quickly. First, we prove 1 implies 2. First, suppose these n vectors are linearly independent. So this is the premise. And by theorem 2, n, which is the dimension of V, is the maximum possible number of linearly independent vectors. Suppose now V is not generated by these n vectors. Then, by the basis extension principle, that's theorem 1, we could find a vector Vn plus 1, let's say, which is not spanned by these n vectors, such that these n plus 1 vectors are linearly independent. But we just said n is the maximum possible number of linearly independent vectors, but now we have n plus 1 linearly independent vectors. This is a contradiction. Therefore, our assumption that V is not generated by these n vectors was false. So it's done. Next, let's prove 2 implies 3. Suppose V is generated by these n vectors. Then we can choose some of these vectors to make a basis of V. Now, by theorem 2, we must choose all of the n vectors because the dimension of V is n. So, this set of n vectors must be a basis of V, and it's done. And this direction, 3 implies 1, is trivial by the definition of the basis because the basis vectors must be linearly independent. So we are done. Now let's move to one of the most important results concerning dimensions of subspaces, the dimension formula. This formula helps us understand the relationship between the dimensions of subspaces, their sum, and their intersection. Theorem 5, the dimension formula, states the following. Let W1 and WB be finite dimensional subspaces of V. Then the sum W1 plus W2 and the intersection W1 cap W2 are also finite dimensional, and this formula holds. That is, the dimension of the sum is equal to the sum of the dimensions of two subspaces minus the dimension of the intersection. Let's walk through the proof of this fundamental theorem. We prove this theorem in 5 steps. Let n be the dimension of W1 and m be the dimension of W2 and r be the dimension of the intersection W1 cap W2. And first step is setting up the basis. Since W1 cap W2 is a subspace of W1 and it's also a subspace of W2, by the way, it is finite dimensional because a subspace of a finite dimensional vector space is also finite dimensional. Now, let this set V1, V2 up to Vr be the basis of W1 cap W2 because R is the dimension of the intersection. And by the basis extension principle, we can choose some other vectors Wr plus 1, Wr plus 2, up to Wn in W1 so that this combined set is a basis of W1. And similarly, we can choose some other vectors Ur plus 1, Ur plus 2 up to Um so that this combined vector, so from V1 to Vr and Ur plus 1 to Um is a basis of W2. And step 2, we set the goal. If we can show that B total, the set defined by these vectors, from V1 to Vr and Wr plus 1 to Wn and Ur plus 1 to Um, if this set is a basis of this sum W1 plus W2, then it follows that the dimension of this sum is given by this. So this R comes from these vectors, and this n minus R comes from these vectors, and this m minus R comes from these vectors. So if we add these together, we have n plus m minus r. So n is the dimension of W1, and m is the dimension of W2, and minus r. This r is the dimension of the intersection. So this is our goal. And to prove that this set is a basis of this sum, we need to prove two things. First, these vectors are linearly independent, and second, these vectors generate this space. We'll prove these in turn. The first is to prove the linear independence. To prove linear independence, we first assume this equality. So this is a linear combination of all these vectors with some coefficients from the field F, A1 to AR, B1 to Bn minus R, and C1 to Cm minus R. And eventually we want to prove that all these coefficients are zeros. To do that, first let's rearrange this equation into this form. So we move this part onto the right-hand side. And this left-hand side belongs to W1 because V1 to VR and WR plus 1 to WN, they form the basis of W1. So they belong to W1. And the right-hand side, UR plus 1 to UM, these are a part of the basis of W2. So this right-hand side belongs to W2. And they are equal. That means both of these sides belong to the intersection between W1 and W2. So let's consider the right-hand side first. So in particular, the right-hand side can be expressed as a linear combination of V1, V2 up to VR because it belongs to the intersection and these vectors are a basis of this intersection, right? So the right-hand side is this, and this is a linear combination of these vectors, the basis vectors of the intersection. Now, let's rearrange this into this form. So we have d1, v1 plus up to dr, vr plus c1 ur plus 1 up to cm minus r um. But these vectors, they form a basis of the subspace W2 by its definition. So they are linearly independent. That means if this equality holds, this right-hand side is the zero vector, that means all these coefficients are zeros. In particular, these c's are zeros, so this is all zeros. So in the original equation, this right-hand side becomes the zero vector. That means this part is equal to the zero vector, so we have this equality now. But now, these vectors v1 to vr and wr plus 1 to wn, they form a basis of the subspace W1. So they must be linearly independent. That means all these coefficients a1 up to ar and b1 up to bn minus r, they are all 0. Therefore, this set, B total, containing all these vectors, this is a linearly independent set of vectors. And step 4 is to prove that B total is a generating set of vectors for W1 plus W2. Now, any element of this sum can be expressed as a sum of two vectors, x plus y, let's say, where x belongs to W1 and y belongs to W2. So x can be expressed as a linear combination of these vectors because v1, v2, and so on, and wr plus 1, and so on, up to wn, they form a basis of w1. And similarly, y can be expressed as a linear combination of these vectors because they form a basis of w2. Now, let's add them together. Then we have this. X plus y is this. So a1, c1, a2, c2, and so on, and b1 and so on, and d1 and so on, we have this. So this is a linear combination of the vectors in B total. Thus, we have proved that W1 plus W2 is generated by these vectors. So in conclusion, B total consisting of these vectors is linearly independent and generates the sum space W1 plus W2, and hence it's a basis of W1 plus W2. And we are done. The dimension formula leads to some important corollaries. The first corollary is this. For a sum of multiple spaces, W1, W2 up to Ws, its dimension is less than or equal to the sum of the dimensions of individual spaces. And crucially, the equality holds if and only if the sum of the subspaces is a direct sum. Okay, let's see the proof. We have just proved the case when S is equal to 2. The rest is a simple mathematical induction. So we will skip it, but we will prove the case when the equality holds. So suppose this sum is a direct sum. Then that means for each I from 2, 3 up to S, we have this. So the intersection between the sum W1 plus W2 up to Wi minus 1 and Wi contains only the zero vector. So this is one of the properties or defining properties of the direct sum. Now, when I is equal to 2, we have this. So the intersection between W1 and W2 must contain only the zero vector. And by the dimension formula, we have the dimension of this sum space is given by the dimension of W1 plus the dimension of W2, because the dimension of the intersection is 0. And when I is equal to 3, we have this. So the dimension of this sum, W1 plus W2 plus W3, is equal to this, because the intersection between this and this contains only the zero vector. And from this, we can split this into this and this. So we have this equality. And we can repeat this over and over, and eventually we have this equality. And now we need to prove the converse. So we assume this equality holds. And let Ui be this sum. So it's the sum of all the subspaces from W1 to Ws except for Wi. Then the dimension of this Ui is less than or equal to the sum of these dimensions. Okay. Now, since the sum of all the subspaces from W1 to Ws is equal to Wi plus Ui, because Ui is the sum of this except for Wi. So if we add Wi, they are the same. Now the dimension of this sum is given by this, because they are equal. And this is less than or equal to the sum of these dimensions. And if we expand this part, then we have this. So it's the sum of dimensions of all the subspaces. However, we are assuming this equality. That means this left-hand side and this right-hand side, they are actually equal. So these are not really less than or equal to, but they are actually equal. In particular, this dimension is equal to this sum of dimensions. So we have this equality, which implies that the dimension of the intersection between Wi and Ui is equal to 0. So that means this intersection, so this is actually Ui. So Ui cap Wi contains only the zero vector. And this is a defining property of the direct sum. Thus, this sum, Wi plus W2 plus up to Ws, is a direct sum. And we are done. Finally, we have this concise equivalence for direct sums. The vector space V is a direct sum of the subspaces W1 up to Ws, if and only if the dimension of V is the sum of the dimensions of the subspaces. And there you have it. We've covered the essential properties of bases and dimensions in vector spaces and derived the powerful dimension formula for subspaces. Understanding these concepts is crucial for deeper work in linear algebra and its applications. If you found this video helpful, please give it a thumbs up, subscribe for more content, and leave any questions in the comments below. Thanks for watching, and see you in the next video. Bye.